at 13.9, I believe it is. So page 120. Let's try and cover some of these, all right? And let me screen share too. Whoops, wrong button. Let's try this one. All right. And so, whoops, get that a little smaller there. Whoops, there it is. All right. Escape from the planet of the physicists. Here we go. You have a, this is my favorite. Everything works okay, but only within 10%, right? And everyone's always assuming everything is a sphere or a point mass. And yeah, okay. People are always making graphs instead of watching TV. So on this planet, let's assume this planet has size m and radius r. So that's this beast right here. Oops. This sucker, this big purple planet has mass m and radius capital R. Okay. And then a few sane individuals seize control of a railgun to launch space pods. The people squeeze into the space pod and are launched from the surface at speed v. Okay, so there they are. They're launched from the surface. They don't care where they're going as long as it's somewhere else other than with the physicists. The railgun has negligible length, so blah, blah, blah. After leaving, drag is negligible. So we're going to ignore air resistance and just assume the only force acting on the space pod is gravity. All right. So to escape, this is something you need to, this is important now. So I've been having a little bit of fun with this problem. Now listen up. To escape, you have to get an enormous altitude with a tiny bit of speed. So if you want to just barely escape from a planet, these are what you assume. You assume that your altitude is approximately infinity and your speed is approximately zero. Think about it. If you got to infinity with a greater speed than that, you would keep going and get farther from the planet. If you have zero speed at some other spot, you're going to go out here and then fall back and you didn't escape. So, got it. We're trying to escape. These are the assumptions you make. Determine the initial launch speed required to escape the planet. All right. Before we do this, before you look at the solutions, take a guess. What type of problem should we do? What type of problem should we do? We have two techniques for this. There's gravity with forces or there's gravity with energy. What do you think? I'll let you think to yourselves. You can chat if you want, whatever. I'll tell you in just a minute. I would do an energy problem. Now, so let's take a look. I'm going to have U initial plus K initial. Do I have any non-conservative forces? No. Assume drag is negligible. And the only force acting on the spot is gravity, right? We'll deal with drag another day. So there's no work that's non-conservative. So we're ignoring the non-conservative work due to drag. So I'm going to set that equal to 0. I keep going. I say there's U final plus K final. And now I'm going to remind this that this is negative G M M over the distance between them. Initially, the distance between them is capital R. Now I have some speed. I have no work non-conservative. This is G M m over what radius? Approximately infinite. And there should be a minus sign, minus sign, minus sign. That's like the most common mistake. You could see even I, with 20 years of experience, sometimes I forget the minus sign. I wasn't too worried about it because if I have 1 over infinity, this is approximately equal to 0. Okay. And then plus, because it's just barely moving when it gets far away, that's going to be a 1/2 mv final squared. That's also going to be 0, approximately. And notice this minus sign right here is pretty freaking important. Otherwise, the problem doesn't make sense. So that minus sign is pretty important. From there, the problem is easy, but I want to pause and make sure people understand how I got there. This is the initial gravitational. This is the initial kinetic. We ignored atmospheric drag, which allows us to set that to 0. I have an infinity. So this term drops out and it's barely moving. I'll get the chat. Go ahead, speak up.
Can you hear me?
Yep.
Okay, so my question is, why exactly are we setting h to approximately infinity? I guess that's really the part I don't understand.
Yeah. Well, the idea is if you get to a very large altitude, at that point, you're so far away from the planet, you could call it infinite. So, like, what if I said it was 100? Actually, let's just say it was 1000 R. What I'm telling you right now is if you said h equals 1000 times the radius, that's approximately equal to infinity as far as the physics goes. And so it just is slightly more convenient for doing the math because it just says set this equal to 0. Another way to say it is you never really escape the planet until you're infinitely far away because the function 1 over r technically never converges, right?
So you're saying that the planet is still always kind of pulling, no matter how far you're getting away, is what you're saying. But you're saying that at a certain point, uh, the distance, the r, is basically becomes irrelevant.
That's right.
Okay.
And I happen to know this problem is hard to understand unless you could see it and visualize it. Conveniently, in lab this week, you're going to do this one. And at the risk of boring you a little bit, let me give you just a second. Actually, I'll show you that after we finish the problem. But basically, everybody's going to code this, and you get a better idea of what it means to escape. And it's really sensitive. So in the third sig fig, I changed the number from like ending in 3 to ending in 4. Like, so it was like 500 something. I don't remember. I don't want to give you the answer because it's the quiz answer, but it was, yeah, basically changing the number from 600 to 601 would make the difference between this thing escaping or not. So it's really sensitive. This gives you that limit. So is that good on that, Nick?
Yeah, we're good.
It gives you the asymptotic limit of truly escaping. All right, so let's call that good. And let's go over and look at the solution, see if there's anything else in there. Looks like, hey, everybody, if you're doing 13.10, looks like I forgot to say use 5.97. So you might make a note that's right below this problem. I saw it right there as I was, sorry about that. So basically use Earth mass for the planet in 13.10. Here's the problem all worked out. So notice, and there's what he was just talking about. If you set that altitude to infinity, this whole side goes to 0. From there, you solve this thing. All right. There's actually some interesting stuff about this. So here's the escape speed from Earth. And now I'm going to come back to this problem right here. So I plugged in these numbers, Watch out, kilometers, kilometers. Okay. Notice here's an AK-47. So if you're shooting an AK-47, the muzzle velocity, the bullets come out at 700 meters per second. Okay. Now compare that to the escape velocity that we just discovered, 11.2. So maybe we shouldn't go around shooting AK-47s in the air. Why? Because the bullets come back down. They are going slightly slower, but easily fast enough to kill someone. So try not to do that tonight, please. All right. Now, obviously, what's interesting is as you shoot them straight up, they'll never kill you, right? Because the Earth is going to rotate by the time, and so it'll kill somebody else unless you angle it just right. Whatever. But yeah, let's stop shooting bullets in the air for fun. That's my advice today. Yeah. All right. Yeah, let's do that. Okay. Oh, let's see what else we've got here. Ooh, this is kind of fun. Lompoc. Yeah. All right, so let's see this. There's some interesting stuff here. Why is it convenient to launch satellites from places like Florida? Florida gave us a huge advantage over the Soviet Union back when it was called the Soviet Union in what was called the space race. It's because it's so far south. If you think about this, I'm going to try and draw this here on the whiteboard, okay? Oops. Let me do this. Let me do it on this one. So if we draw a planet, all right, and you think about, I'll try and draw the equator here. Right? So let's say that's the equator, all right? And now if this planet is rotating about this axis, if it's rotating here, think about this. If you launch a satellite right here, you're actually only going around in this circular radius. If this is omega, you have some speed right here. V equals R omega. Notice the closer you get to the equator, the bigger your radius is. So that gives you more initial speed. That means you need less rocket fuel to go into space. So if you're launching at the equator, you start out with this much kinetic energy. So think about Florida dipping way down there. You're going to have a huge advantage launching from Florida than you would from the southernmost point in Russia. So, and it's simply, you just have more initial kinetic energy. And so that gets you that much closer to getting into orbit or escaping the planet or whatever you want to do. So that's what that's all about. The closer you are to the equator, the more initial kinetic energy you have, the easier it is to launch something into orbit. You just have more initial energy. So that's that part. Let's go back to the other one. So there we go. Lompoc is interesting because it's used for polar orbits. Some of you probably have relatives that work on the base and know a lot more about it than I do. But yeah, that's cool. If so, you could share your experiences in the chat or whatever you want to do. That's very fun. But yeah, there's a reason that Lompoc is pretty much always going to stay in business. All right, that's cool. So now here's something. Think about this. We just discovered the escape speed. I want to go look at that number really quick. It's right here. That gives you the escape speed from a planet. Now think about this. You could work this out a different way. What if you set this to the speed of light? That gives you a constraint on essentially the density of the planet, right? Mass per unit radius, that's density. So if you have enough mass in a small radius, you could get a black hole where light cannot escape. And this math, you might be saying, does this math even work for that? It turns out this math is valid as long as your black hole is not rotating. So this is called an irrotational black hole. Sometimes that's called a Schwarzschild black hole. All right. So notice if you use the Earth's mass, the radius of the Earth would have to be 1 centimeter to make a black hole. That cracks me up. All right. So yeah, we're not worried about the Earth becoming a black hole anytime soon. And our sun is not going to do that either, if I remember correctly, but that's not my, yeah. All right. So I think that's pretty good with that. It's really interesting stuff, but let's focus on what's going to help you pass. Okay, that's good. This problem is really cool. If you're wondering how to handle elliptical orbits, this shows you. And notice I put this mass in here. If you notice on your problem, I forgot that. So please write that in there right now for 1310.